Okay, antiderivatives. So you should have seen antiderivatives before this class, so this is just a review. Okay, so recall the derivative of a function gives us information about the rate of change of that function. The reverse of finding a derivative is called antidifferentiation. So definition, if capital F prime of x equals little f of x, okay, recall this is the notation used for the derivative, that prime notation, so this is the derivative of the function capital F. If the derivative of capital F equals little f, okay, then capital F of x is called an antiderivative of little f of x. Okay? And then just a note, if you see this notation, g prime of x, this represents the derivative of little g. Okay? An antiderivative of this function would just be written without the prime. It would just be g of x. Okay? So for example 1a, okay, for the function capital F of x equals x squared, this is an antiderivative of 2x. Okay? And this is an antiderivative because if I take the derivative of x squared, I'm going to get 2x. So since capital F prime of x, the derivative of capital F equals, if you recall your derivative rules, bring the power out front to multiply and then subtract 1 from the power. So this would be 2x, which is little f of x. Okay, so x squared is an antiderivative of 2x because when I take the derivative of x squared, I get 2x. Okay, for b, the function x squared plus 5, okay, this is also an antiderivative of 2x, and again, because if I take the derivative of this, I'll get that. So since the derivative of capital F here would be 2x is the derivative of x squared plus the derivative of 5 is 0, so I just get 2x, which is my little f. Okay, so we have two antiderivatives of this function. And in fact, for example 2, if c is any constant, then any function of the form x squared plus c is going to be an antiderivative of 2x. In that sense, if I take the derivative of any function of this form, I'm going to get 2x plus derivative of any constant is 0. So I always get 2x, which is little f of x. Okay? All right. And in fact, all antiderivatives of a function only differ by a constant. Okay. So if capital F and capital G are both antiderivatives of little f of x, then the difference between the two is just some constant, okay, for some constant c. Or you could write capital F of x equals capital G of x plus some constant. So in other words, if I have one antiderivative, I can get to another antiderivative by adding some particular constant. Okay? Okay, the indefinite integral. So we call capital F of x plus c the family of antiderivatives of little f of x, where c represents an arbitrary constant or all possible constants. And we write the indefinite integral of little f of x with respect to x equals capital f of x plus c. Okay, so the family of all antiderivatives of this function can be found by take one antiderivative and add all possible constants, and you'll get the family of antiderivatives of this function. Okay, this notation right here is called the indefinite integral of f of x. This symbol is called the integral sign, and the function that you have in here is called the integrand. Okay, so for example 3, let's just write out a couple of them. So I'll say example 3a, okay, using the function above, the function 2x, okay, the indefinite integral of the function 2x with respect to x, okay, equals, I just need one antiderivative. So in example 1, we saw I had two antiderivatives. I had x squared and then also x squared plus 5, but let's just pick the simplest antiderivative, the one in which the constant is 0. Okay, so I just need one antiderivative. I'm going to use x squared, okay, and then if I add all possible constants, I get the family of antiderivatives of this function. Okay, let's do another one, b. So let's say we have the constant function 5. the indefinite integral of the constant function 5 with respect to x. Okay, this would be, I need one antiderivative of 5. An antiderivative of 5 would be 5x, because if I take the derivative of 5x with respect to x, I just get 5. So here's an antiderivative of that. Add all possible constants to get the family of antiderivatives. Let's do another one. See? Let's say I have the function 2ax, okay, and I want the indefinite integral of this with respect to x. Okay, so that's telling me that x is the variable, okay, and so an antiderivative of this would be ax squared. Okay, so if I take the derivative of this function, I know this is an antiderivative of that, because if you take the derivative of this function, recalling your rules, I'm treating a as a constant because x is the variable. That's what this is telling me. So my a is just a constant, so I'll keep that constant times the derivative of this would be 2x. So a times 2 times x, there's my 2ax. I just switched the order of the 2 and a. Anyways, this is an antiderivative of this with respect to x. Add all possible constants to get the family of antiderivatives. Okay, now note the dx that we see here is telling us that we are integrating with respect to x, meaning that we're treating x as the variable. Okay, so just like just on a side note, you don't have to write this, but if you recall the notation dy dx when you were taking derivatives, this told us that we were taking the derivative of the function y with respect to x, so x was our variable. Okay, here it's the same thing. It's telling us, the dx is telling us which variable we're integrating with respect to. So for example 4, okay, so I'll do a couple of these. Let's say for 4a, let's go back to that constant function 5. Okay, so if I'm integrating 5 with respect to x, x is the variable. Okay, an antiderivative of 5 with respect to x would be 5x, because if I take the derivative, I will get 5. Okay, and then of course indefinite integral, add all possible constants. For b, if I wanted the indefinite integral of 5 with respect to y, okay, then y is the variable, so I would get 5y as an antiderivative. Okay, the derivative of 5y with respect to y would be 5. Okay, so, but indefinite integral, add all possible constants. Let's do a few more. For c, let's say we wanted the indefinite integral of 5 with respect to a. So now a is my variable. So an antiderivative of 5 with respect to a would be 5a, and then add all possible constants for the indefinite integral. Just a few more, just because in previous classes I know that I've seen a little bit of confusion when students see A's and B's and R's, and just making sure we know what to treat as the variable that we're integrating with respect to. I just wanted to make sure we pointed this out. So let's do just a few more. Let's say the indefinite integral of 2ax with respect to x. Okay, so this is my function here, 2 times a times x, but this is telling me that x is the variable. Okay, an antiderivative of this with respect to x would be ax squared. Okay, and that's because if I take the derivative of ax squared with respect to x, I'm going to get 2ax. Okay. And then if I wanted the indefinite integral of 2ax, but now with respect to a, now a is the variable. and then I'm going to treat 2x as a constant. Okay, so in this case, an antiderivative of 2ax with respect to a is going to be xa squared. Okay, and you can check it. If I take the derivative of this with respect to a, x is a constant now, so I'll keep my constant, and then the derivative of a squared with respect to a, bring the 2 out front, subtract 1 from the power. So again, I get x times 2 times a, or rearranging 2ax. Okay. So I don't mean to confuse or anything like that for anyone, but I just want to make sure that we understand what the dx or dA or whatever you see, it's telling us which function is the variable and which ones we're going to treat as constants. Okay, so these would be constants, that's the variable. In this case, this is a constant, and in this case, x is going to be a constant. We're going to treat it as a constant, okay? And a is the variable.